All right, welcome to lecture 9. Today, we're going to be switching gears. For the past little while, we've been talking about derivatives in multivariate calculus. Today, we're going to be switching to talking about integration and integrals for functions of several variables. So let's go back a little and let's think about and talk about what goes on in single variable calculus to get warmed up. So we have single variable integrals, and they calculate area. When we have a curve, what the single variable integral is supposed to do, it's supposed to calculate the area that lives between the graph of a function and the x-axis, this flat horizontal line. And our main calculational tool for them is the antiderivative. When we have a function we want to integrate, we take its antiderivative, something whose derivative is equal to that, and evaluate it between the kind of left and right-hand ends of the region we want to calculate the area of. And this is a procedure that hopefully we at least remember, even if we haven't done it for a little while. But there's some small things that we have to be aware of when we're doing single variable integration. The first of those is that it doesn't 100% calculate area if we use this antiderivative method. Namely, we have to be aware of the fact that if we have a function that dips below the x-axis, the area that's below the axis but still between the axis and the graph counts negatively, and the area that's above the graph counts positively. So it's kind of actually a difference of an area above the graph and an area below the graph. So that's the first thing to be aware of. And the second thing is that, when we're mechanically doing this integral by finding an antiderivative, we get some kind of odd rules. Like if we take the limits of integration and switch them, what happens is that we get an extra negative sign out in front. This doesn't seem like a huge deal. Some of it is just fooling around, but this separation into the thing we want to calculate, this area calculation, and the method we actually use to do it, calculating an antiderivative, has a much wider deviation when we talk about integrals for functions of several variables, depending on what we want to calculate. So our goal is still basically the same for integrals with several variables. One of them is that we just want to put together a bunch of contributions into a total contribution of some type. But when we have different problems, we're going to need to be careful and say, this type of problem requires this integration procedure, and this other type of problem requires another integration procedure. So to be a little bit more specific about that, let's talk about the types of problems we're going to see in this class. The first few are problems where we may have already seen some of them before, like if we have a path, if we have a curve inside two-dimensional or three-dimensional space, maybe we want to know the length of that path. And there's a way to calculate that using an integral. If we have a surface that's sitting inside three-dimensional space, maybe we want to know the area. Or if we've got a three-dimensional shape sitting inside three-dimensional space, maybe we want to know the total volume. Or all of those have variance, where if we've got some kind of substance like a wire or some kind of sheet that's made of a material, and the material is maybe heavier in some parts than in others, we can use these types of integrals to calculate things like mass. And in general, these three types of integrals are calculating like a total amount of something. So they're telling us about how much there is in total. But there are another couple of things that we're going to be interested in. Like the first is the change in energy when we're moving along a path. So sometimes if we're moving around inside space and there's a fluid flow that's trying to push us in various directions, or there's a magnetic field that's trying to push something we're carrying, we either kind of, in total, we fight against it, or we are carried along by it. It either grants us energy or it takes energy away from us. And so that's the first type of integral we'll see along paths inside space. And similarly, if we've got a surface and there's a fluid flowing, then some of it flows through the surface in some parts and some flows the opposite direction with different speeds and different strengths. And we'd like to know maybe the total amount of fluid or the total rate of change through the whole thing. And these two types of integrals are, in rough, they're measuring total change. And there are different procedures for analyzing the integrals that we see on the top and the integrals that we see on the bottom. And we are going to have to keep track of those when we're encountering them in this class.